Let's talk about something the AI industry does not want to discuss. Every AI coding tool today, every copilot, every agent, every chatbot bolted onto an IDE has the same fundamental dependency: context. The quality of AI's output is bounded by the quality of the context it receives. Feed it the wrong context, it produces confident garbage. Feed it too much, it drowns in noise. Feed it too little, it hallucinates to fill the gaps confidently. For an individual developer working on a small project, context management is simple. The code base fits in a context window. The developer knows the architecture. The AI reads a few files, makes suggestions, and the developer evaluates them against their own mental model. This works. But enterprise software is not a small project. In a typical enterprise, there are hundreds of code repositories across dozens of branches, if not hundreds. These repositories represent different components, different versions, different generations of the same product. Over the years, different developers with different expertise, different styles, different technology preferences have contributed to this code base. It has gone through architectural transitions, framework migrations, team reorganizations. The code that you see today is actually a product of a complex history that no single person fully understands. And the code is only the beginning. Around it exists an entire ecosystem of enterprise data. Thousands of pull requests, tens and thousands of commits, years of Jira tickets and backlogs, CI/CD pipelines, release histories, security audits, architecture decision records, team wikis, onboarding guides, vendor documentation, regulatory compliance artifacts. This data has deep interrelationships. A commit in one repository might relate to a Jira ticket in another project, which references a security audit that constrains how a third component can be modified. This is the enterprise context landscape, and it has the same characteristics as any big data problem: volume, variety, and velocity. Thousands of artifacts, multiple formats and sources, continuous change. The question is, how do you make this context available to AI agents in a way that it actually works in an enterprise setting? The first instinct is the most obvious. Just connect everything. Wire up your Jira via MCP, expose your Git history through a REST API or an MCP, give the agent access to your code review tools, your wikis, your CI/CD pipelines. Let the AI figure out what is relevant. This is the raw exposure approach, and it is the default assumption behind most AI tool integrations today. It sounds democratic. Give the AI access to everything. Trust it to find what matters. It does not work at enterprise scale. An AI agent receiving access to 5,000 Jira tickets, 12,000 commits, and 300 repositories cannot deterministically identify which 15 artifacts are relevant to the task at hand today. It will sample, it will guess, it will retrieve based on keyword similarity, which misses semantic knowledge. It will treat a 2019 architectural decision with the same weight as a 2024 one, because it has no sense of which supersedes which one many times. The result is probabilistic contextualization. The AI might get the right context or it might not, and you have no way to know which happened until you see the output. For individual productivity tasks, this is acceptable. For enterprise grade work, where an incorrect architectural assumption propagates through a 20-phase migration, it is catastrophic. The industry's response has been to build intermediate knowledge layers, systems that crawl your enterprise data sources, construct a complex graph of entities and relationships, apply embedding models and graph RAG techniques, and expose this indexed knowledge back to AI agents through APIs and MCPs. This approach has merit. It addresses the volume problem through indexing. It addresses the variety problem through entity extractions. It surfaces relationships that raw API access would miss. But it introduces its own problems. And the deepest ones are architectural, not operational. First of all, RAG is inherently probabilistic. The moment you introduce retrieval augment generation, whether vanilla vector RAG or graph RAG, you have introduced a probabilistic selection step. Embeddings compute similarity, not correctness. A chunk about authentication timeout handling might embed close to session management, but miss the critical architecture constraint that authentication must route through a specific gateway. Graph RAG improves this by traversing entity relationships. But the traversal still uses heuristics, which edges to follow, how many hops, what relevance thresholds to apply. Every one of these decisions is probabilistic. You get probability relevant chunks, not the right context. For search and Q&A, this is fine. For simple projects, simple problems, this is fine. For engineering execution, where the wrong architecture assumption propagates through 20 phases of a migration, probably relevant is not an engineering guarantee, which we need. Second is agent indirection. Evolve towards agentic search, agents that reason over graph rather than just retrieve. These are their agents, the middle layer, not yours. Your consuming agent, the one actually writing code, executing a migration, enforcing guidelines, does not get to control the search strategy. The flow becomes your agent formulates a query, the intent. This intermediary agent or a group of agents interprets this query within their system's boundaries. Their graph returns what it considers relevant through probabilistic traversal, and your agent receives whatever survived that pipeline. Two levels of interaction. At no point did the architect, the person who actually understands what this specific task needs, have direct control over what the consuming agent sees. And third, generality over specificity. These systems build knowledge graphs for general purpose search. They answer, find me everything related to authentication. But they probably cannot answer for this specific migration, what are the 3 architectural constraints that the backend team established in Q2 that the front-end team does not know about yet. That requires curated judgment, not search. And fourth, no enforcement. Even if the graph surfaces the right context, there is no mechanism to ensure that the AI uses it correctly. How deeply should the agent read it? Should it be injected directly into the prompt? Should it be treated as a mandatory guidance or optional reference? Knowledge graphs has no opinion. It retrieves, it does not prescribe. For many cases, internal search, employee onboarding, journal Q&A, this approach works well. But for engineering execution, where context must be curated, versioned, traceable, and enforced, it is either insufficient or overkill, often both. Now, to be precise about the boundary, because we are not saying these approaches are useless. Real-time retrieval of a specific known item is a solved problem. What is the current status of a Jira ticket of this project 1, 2, 3, 4? What are the latest CI/CD results for this branch? Show me the deployment log from last night. These are point lookups, MCP, REST, direct tool access. They handle this perfectly. The item is specific or a group of specific items. The answer is a fact, and you need the live current value. The problem begins when you move from lookup to analysis. What architectural patterns has this team established over 2 years? Which areas of the code base have the highest defect density and why? What constraints from the security audit apply to this migration? These kind of questions and analysis require reading hundreds or thousands of artifacts, synthesizing patterns across them, relationships, applying judgment, and producing knowledge that shapes engineering decisions. This is where probabilistic retrieval breaks down, because the answer is not a single item waiting to be fetched. The line is clear. Lookup goes to the source in real time. Analysis must be curated, versioned, and enforced. The mistake is treating both as the same is the problem. So what is actually needed? Current systems solve context discovery but not context governance. Find relevant information but not ensure the right information is used in the right way by the right agent at the right time. The fundamental distinction is this. In the RAG model, the architect can tune parameters, adjust thresholds, configure graph schemas, weights, certain entity types, but can never guarantee what the consuming agent sees. In a governed model, the architect defines what the agent sees. That is the difference between configuration and governance, between probability and determinism. What enterprise AI engineering needs is a system where architects define what matters, not algorithms, where consuming agents read curated artifacts directly, not probabilistic chunks through intermediary agents, where context is shaped for its purpose, freshness is measurable, lineage is traceable, and consumption is governed. This is what SASVA's context management does. It treats context not as a retrieval problem, but as an engineering discipline. At the center of the system is a context registry, a structured catalog of every knowledge artifact that has been produced, imported, or curated for the workspace, not a flat file listing, a typed, versioned, relationship-aware catalog where every entry carries provenance, what it is, where it came from, how fresh it is, how agent should consume it, and what lineage produced it. This catalog lives in the workspace alongside the code, versioned, portable, inspectable. The system recognizes that different types of knowledge require fundamentally different acquisition, different management, and maybe different consumption strategies. A developer's style preference is not the same artifact as a 7,000 node dependency graph. Treating them identically is a design error. The taxonomy spans the full spectrum of enterprise knowledge. Product documentation governed by AI agents that systematically explore your code. Code archaeology that investigates other version control systems history to understand how specific problems evolved over time. Not reading the current code, but reading the code's biography. Issue tracker intelligence that synthesizes patterns from project management data, not listing tickets, but identifying which areas generate the most defects and why. External data pulled from outside systems via API, stored locally, then analyzed. Repository guidelines extracted from what the code actually does, not what the README claims. Dependency graphs mapping structural relationships. The X-ray of your code base. Human authored guidance capturing the things that exist in architects' heads but never make it into documentation. Imported documents, PDFs, presentations, wiki exports, converted and indexed alongside AI generated artifacts. And then there is derived analysis. And this is where it gets interesting. Any existing context can be used as the source for a new focused analysis. Take your 200-page product documentation and derive a 15-page security focused brief. Take your archaeology report on memory leaks and derive a remediation playbook. Take your issue tracker analysis and derive a sprint risk assessment. Each derived context inherits lineage from its parent, but it is focused by a specific human intent. This is not a hierarchical filing. It is knowledge composition, building new understanding from existing understanding with full traceability. In an enterprise with dozens of active contexts, a critical question emerges. Where did this knowledge come from, and is it still trustworthy? If your sprint risk assessment was derived from an issue tracker analysis that was pulled 3 weeks ago and 47 new tickets have been created since, maybe that risk assessment is stale. But you can only know that only if you can trace the lineage. The system renders context relationships as directed acyclic graph across three conceptual layers. Source of truth, examples being your code base, Git history, Jira, GitHub API, human expertise. Primary context, the first order knowledge artifacts produced from these source of truths. Product documentation, archaeology reports, tracker analysis, dependency graphs, and then derived contexts, second order and deeper artifacts, security briefs from product documentation, remediation guides from archaeology, risk assessment from tracker reports, and then derived, a sprint planning guide derived from a risk assessment, which was actually derived from a tracker analysis. Every edge is a provenance relationship. Every node carries a freshness signal. An architect looks at the graph and immediately sees, oh, our security brief is stale because the product documentation it was derived from were regenerated last week. The brief needs to be rederived. There is not a gas. That is traceable, computable fact. The power of this model grows with depth. A team pulls 5,000 GitHub issues, AI produces an issue analysis, a security lead derives vulnerability patterns, a sprint planner derives a remediation backlog. 3 levels of derivation, each traceable back to the source. If the issues are repulled because 200 new ones were filed, the stillness propagates up the entire chain. The architect rederives what needs updating without rerunning the full pipeline. Basically, build once, derive many, refresh selectively. That is compositional knowledge management. Now, briefly, let's also talk about freshness. Because in traditional knowledge management, freshness is a matter of opinion. Someone checks a date and makes a judgment call. That does not scale. The system replaces judgment with measurement. Each context types has a specific stillness computation. Code-based derived contexts are fingerprinted at generation time. File path, sizes, hashes, and compared against the current code based on query. For example, 47 files changed since last generation. Similarly, derived context fingerprints their parents' files at derivation time. If the parent updates, the data is stale. External data contexts compare collection timestamps against analysis timestamps. Dependency graphs track new or modified source files against the graph fingerprint. Every context carries a computationally derived freshness signal. No guessing, no meetings about when did we last update the docs. And because stillness propagates through the lineage graph, a single change at the source level, say a major refactoring, surfaces its impact across all downstream derived context lineage graph and nodes. The architect sees the full blast radius of the change, not just the immediate effect. This turns stillness from information into a governance signal. The input to policies about when to refresh, when to block, when to rederive. And now we come to enforcement, and this is where the system departs from everything else. Most AI context systems stop at retrieval. They make information available and hope the AI uses it well. SASVA introduces enforcement, a governed model for how agents consume context, controlled by the architect, not by the AI's inference. The insight is simple but profound. Not all context should be consumed the same way. A 3-paragraph team convention about naming standards should be injected maybe directly into the prompt. It is small, it's critical, and the agent should follow it literally. We can enforce it in our orchestration layers. But a 200-page product documentation set should not be injected. It would overwhelm the context window. Instead, the agent should explore it systematically, reading sections relevant to the task at hand. Context consumption exists on a spectrum defined by 2 independent dimensions: depth, how thoroughly the agent should explore the context, and strategy, how the agent should structurally approach the content. On the depth axis, the spectrum runs from direct injection, the content placed directly into agent's prompt as mandatory instruction, to deep autonomous exploration, where the agent is given a substantial budget to cross-reference, compare, and synthesize across a large knowledge artifact. Between these extremes, bounded scanning, target section reads, structured sampling, these are calibration points on a continuous axis, not a fixed taxonomy. New consumption modes emerge as the science evolves. Modes tuned for content shapes, task types, trust levels, multi-pass reading strategies. The strategy axis is equally important. The same depth budget applies differently depending on the content shape. Structured documentation invites section-based navigation. Read the index, drill into specifics. A dataset with thousands of records invites sampling. A dense report invites sequential reading with selective depth. A dependency graph invites query-driven exploration. The system computes both dimensions dynamically from the content's actual characteristics, file count, size, format, structure. The architect doesn't configure tool call counts. They express a consumption philosophy. This is critical. Inject it versus this is deep background, let the agent mine it. And the system translates that philosophy into an operational plan calibrated to the content. This is the core science, matching the agent's reading behavior to both the nature of the knowledge and the architect's intent for how it should influence the work. The spectrum grows richer over time. Modes sensitive to task phase, to agent role, to confidence thresholds. The underlying principle remains constant. Consumption is governed, not left to inference. And this matters because it answers one of the hardest problems in agentic AI. How do you balance context completeness against context window utilization? Too much of context and the model loses focus. The critical instruction drowns in noise. Too little and the model hallucinates. The architect, the person who understands both the knowledge and the task, makes this judgment at the architectural level. Set it once, enforce it consistently across every agent interaction. This creates a new role for technical leadership. In traditional AI-assisted development, the architect's influence ends at the design document. They write the architecture spec, hand it off, and hope the developers and their AI tools will follow it. SASVA introduces the architect as the context curator. The architect doesn't just document the architecture. They curate the knowledge artifacts. They will shape how AI agents understand and work within the architecture. They decide which knowledge artifacts should exist and from what sources. They derive focused analysis, adding human intent as a lens. They assign consumption modes. They set freshness policies. In team workflows, they map specific context, specific phases, and team members. The database migration phase reference and data layer archaeology, while the UI phase reference component docs and design system guidelines. Each phase gets the right knowledge, not all knowledge. They get what matters. These decision compounds over time. The workspace accumulates a rich, curated, interlinked knowledge state. New team members inherit the entire context graph. New tasks don't require rediscovery. The architect's curation becomes organizational memory, queryable by both humans and agents, with full provenance and freshness guarantees. Enterprise knowledge does not exist in one place. It is spread across code repositories, issue trackers, wikis, API services, monitoring systems, compliance database. Getting into usable form requires structured acquisition pipelines. not raw API calls. For knowledge that lives in the code, the system runs AI workflows that systematically explore the code base over dozens of tons, understanding architecture, tracing dependencies, discovering conventions, mapping structural relationships, extracting implicit patterns. The output is structured artifacts suitable for governed consumption by downstream agents. For knowledge that lives outside the repository, the external knowledge, the system supports pull-based acquisition pipelines. Each source is defined declaratively. Endpoint, authentication, pagination strategy, item limits. The pipeline executes the pull, stores raw data locally, and then runs an AI analysis pass to produce a report. This is fundamentally different from real-time API access. A live API returns unpredictable volume, relevance, and latency. An acquisition pipeline produces a curated, analyzed, locally stored artifact with known contents and known freshness. The architect defines the pipeline. The system executes it. The output becomes a versioned context with stillness tracking. Acquisition operates on two triggers: scheduled refresh cycles for evolving data and event-driven updates. Webhook triggered refreshes when upstream sources change. A commit triggers doc reevaluation. A new sprint triggers tracker reanalysis. A security advisory triggers dependency rescan. Same deterministic output either way. As the knowledge state grows, agents need a way to navigate it efficiently. The system maintains a context index, a structured catalog with metadata, summaries, tags, and lineage that serves as a triage layer. Agents scan the index to identify relevant contexts before reading actual content. The index operates at multiple levels: keyword and tag-based triage for structured queries, and embedding-based similarity search for semantic discovery. Critically, all discovery operates over curated, versioned, governance, tracked artifacts, not raw enterprise data dumps. Let me circle back to derived context because the science here is worth dwelling on. Enterprise knowledge is naturally pyramidal. At the base, raw data, thousands of commits, issues, files. In the middle, we may have structured analysis, product documentation, archaeology reports, tracker studies. At the top, focus artifacts, security briefs, remediation guides, sprint risk assessments. Each level compresses the level below it, applying human intent as a focusing lens. Derived contexts are the mechanism for this compression. And because each derivation is registered with its parent and its intent, the compression is traceable and reversible. If you need to understand why the remediation guide recommends a specific fixed pattern, you trace back to the archaeology report, then to the Git history. Nothing is lost. It is compressed, not discarded. Derivation is also economically efficient. Full product documentation requires AI to explore the entire code base. Expensive. Deriving a focused brief from that document requires exploring only the existing documentation, a fraction of the cost. Architects create many derived contexts from few primary contexts, each focused on a different concern. Security, performance, testing, onboarding are some examples. The primary context is generated once and becomes the foundation for a family of focused derivatives. When the knowledge spans multiple sources, the API docs live in a product docs. The deployment constraints live in an important manual. Merge mode derivation combines multiple parents with an explicit conflict priority. Which source wins when they disagree? The architect decides. Conflict resolution by policy, not by algorithm. Let me trace how all this comes together in practice. An architect generates product documentation from the code base and pulls 5,000 GitHub issues through an acquisition pipeline. From the product docs, they derive a security brief. From the issue analysis, a team lead derives vulnerability patterns. The lineage graph now shows two derivation chains: code base through product docs to security brief, and GitHub API through issue analysis to vulnerability patterns. The architect sets consumption modes. Security brief gets deep reference because it's dense and critical. Product docs get bounded context reference, large but structured. Team preferences get injected directly, small and mandatory. The dependency graph gets bounded reference, query driven. When a developer starts a migration task, the orchestration engine assembles context for each phase based on the architect's selections. Planning receives the product docs and dependency graph for reference. Security review receives the security brief for deep exploration. Implementation receives team preference, inline and product docs for light reference. Verification receives the vulnerability patterns for deep reference. Each phase agent receives exactly the context the architect specified in exactly the consumption modes the architect chose. The agent does not decide what to read and how to use. The architect decided. It was reviewed. The system enforces. This is the determinism guarantee. In a raw exposure model, the agent's context is probabilistic. It depends on what the retrieval algorithm returns. In this model, the agent's context is deterministic, defined by the architect, governed by the registry, enforced by the runtime. The architect can audit exactly what each agent saw, trace every decision back to its context source, and reproduce the execution with the same context. Context as a governed input, not a side effect of a search. At scale, the system adds further intelligence. Context-aware agent, routing maps task semantics against curated index, automatically weighting relevant context for each task. Cross-workspace federation enables controlled sharing of context artifacts across team workspaces with the same lineage, staleness, and governance. Context impact analysis predicts which contexts a proposed code-based change will affect before it happens. Nor is this stale, but this change will make these artifacts stale, and here is the downstream impact. Adaptive consumption budgets learn from observed agent behavior, which sections agents read, which they skip, and refine the heuristics, closing the loop between prescription and practice. And context quality scoring evaluates accuracy beyond freshness. Do the documented APIs match the actual APIs? Do the guidelines reflect current patterns? Not just, is this fresh, but is this correct? The thesis of SASVA's context management is this. In enterprise environments, context is too complex and consequential to be auto-discovered. It must be architect curated, version managed, and engine enforced. 3 pillars. Curation. Architects define what knowledge exists, how it relates, and what intent focuses. The context state is a designed artifact, not a crawled index. Second, form. Each context is shaped for its purpose. Inline for critical guidance, structured docs for exploration, report for deep analysis, derived briefs for focused application. The form is chosen by the architect to match the consumption need. And third, enforcement. The runtime guarantees that agents consume context as prescribed. Not context is available, context is injected, budgeted, and governed according to the architect's specification. Together, these 3 pillars transform context from a retrieval problem into an engineering discipline. The same rigor that enterprise teams apply to the code architecture, deployment pipelines, and testing strategies now applies to the knowledge that shapes AI behavior. The result, AI agents with the right information, in the right form, consumed in the right way, with full traceability back to its source, not because they figured it out, because an architect designed it that way. That is the difference between AI that generates and AI that delivers. And it starts with getting the context right. Thank you.